All right, I think we're ready to start. So we're continuing on where we left off, on geodesics and Kerr. So we had written down 3 constants of motion for geodesics in terms of killing vectors and this killing tensor. And just like in Schwarzschild, we also have the conserved length, G alpha beta, U alpha, U beta equals -1. So just like in Schwarzschild, we can now use these equations to solve for T dot, R dot, R dot will come from this, theta dot, and phi dot. So as just an example, for E and LZ, you can write minus UT as minus GTT T dot. T dot is a proper time derivative of T minus GT phi dot. So you just write everything in terms of things with indices up. So T dot, R dot, theta dot, phi dot. And then solve for those, and what comes out. So you solve for T dot, R dot, theta dot, phi dot. And we get 4 equations. Remember, the sigma was just the function of r and theta that appears in the metric. I won't write them all out because they get kind of long, but just as an example, this is the equation for T dot. Remember, delta was the other function that appeared in the metric. Okay, so we have a pretty long, ugly-looking equation for T dot. But the important thing to see is that everything on the right-hand side only depends on r and theta. There's no dependence on t or phi. So I'm just going to define this right-hand side to be vt, which is a function of r and theta. Now from this equation, we get an equation for r dot, or rather for r dot squared. And so I won't write out what it is, but the key thing is that it only depends on r. It doesn't depend on even theta. It only depends on r. Then for theta dot, we get some function only of theta, no dependence on r. And finally, we have equation for phi dot. And here we have, on the right-hand side, a function of r and theta. So it's a little bit of a lie saying there's no dependence on theta here or r here, because there is hidden inside this sigma. So the left-hand sides of all these equations depend on r and theta. But you see it always comes in this particular form where it's just a sigma times a dot of a coordinate. So we can then introduce a new time parameter, called lambda, and it's defined to satisfy d tau, d lambda equals sigma. So now on each term here we have d tau, d lambda multiplied by, for example, dt, d tau. So we can cancel the taus and just be left with lambdas. Carter introduced this time parameter lambda, but very often It's called Mino time, just because Mino made a lot of use of it in cell force analyses. So in terms of this new time, we have dr d lambda squared is just Vr of r. We have d theta d lambda squared is v theta of theta. So the point is, this is now decoupled the r and the theta motion. R only depends on r, or rather r dot only depends on r, and theta dot only depends on theta. So the radial and polar motions decouple. And this equation is basically exactly the form that we had in Schwarzschild. So again, we want bound orbits that are, have a maximum radius and a minimum radius. And the turning points are where dr d lambda squared is 0, and so it's when Vr of r is 0. But now we also have the same thing for theta. We're going to have a turning point wherever v theta of theta is 0. So this corresponds to where you're turning around after reaching a maximum radius or a minimum radius. This corresponds to turning around when you reach a maximum polar height or minimum polar height. So we can now write down parameterizations similar to what we did in Schwarzschild. We introduce another parameter called psi r. And we're going to express this in just the same form we did in Schwarzschild. So psi r is a periodic phase. So when it goes from psi r to psi r plus 2 pi, you get the same value of r back. And again, we have, just like in Schwarzschild, that our max is Pm over 1 minus E, and our min is Pm over 1 plus E. And these, our min and our max, satisfies Vr at our min is 0, and Vr at our max is 0. So these two equations become equations for P and E in terms of how we had expressed Vr, which would have been expressed in terms of these other constants of motion, E, Lz, and C. So now similarly, we have same kind of thing for psi theta. We're going to write it in a somewhat unintuitive form, where cos theta is cos theta max, the maximum value of cos theta, times cosine of some other new phase. So again, this is doing one complete polar oscillation when psi theta goes from 0 to 2 pi, or from psi theta to psi theta plus 2 pi. So now we have two phases. Psi r and psi theta. So putting this together, we have r of psi r and theta of psi theta. And we now need to express psi r and psi theta in terms of the Carter variable, or Carter parameter lambda. So we started off with everything written in terms of lambda, and we need to express these new time variables in terms of lambda in order to be able to solve for all the coordinates as functions of lambda, or ultimately as functions of proper time. So we find we find lambda as a function of psi r, and lambda as a function of psi theta. So we specify a value of psi r, that gives us a value of r, and now we want to find the corresponding value of lambda at that value of r. And similarly, we specify psi theta, that gives us a value of theta, and we want to find the corresponding value of lambda. So we find these from just using the chain rule. D lambda d psi r is d lambda dr times dr d psi r. So we have d lambda dr is just 1 over the square root of vr, and dr d psi r is just the derivative of this with respect to psi r. So putting that together, because there's a square root, we have a plus or minus sign. We have 1 over square root of vr coming from the d lambda dr, and then dr d psi r. And similarly, d lambda d psi theta is d lambda d theta d psi theta. So there we actually have cos theta, so you can rearrange this as a function of cos theta rather than theta. But the important thing is, again, that d lambda d theta introduces 1 over square root of v theta. So everything ends up in terms of these v's. So we have plus or minus 1 over square root of v theta times d theta d psi theta. So putting all this together, we get r as a function of lambda and theta as a function of lambda. Now we need also to get t and phi as functions of lambda. We need t as a function of lambda and phi as a function of lambda. But we get those from r as a function of lambda and theta as a function of lambda. Because over here in the equations for phi dot and t dot, you know the right-hand sides as functions of lambda as soon as you know r and theta as functions of lambda. So then you can just integrate that equation to get phi as a function of lambda and t as a function of lambda. Okay, so now we have more phases. So we have psi r and psi theta, and you can also think of an azimuthal phase, which is corresponding to phi. And so now we have what I said originally, which is we have triperiodic orbits. So we have a frequency associated with psi r, a frequency associated with psi theta, and a frequency associated with the azimuthal motion in phi. Now this leads to interesting consequences. So the radial motion has a period which is written as lambda r, and it's just the amount of time in lambda that passes over one complete cycle of the radial motion. So you go from a minimum to a maximum you calculate the amount of time in lambda that takes, and then you double it to go back from the maximum to the minimum. And this is 2 times the integral from our min to our max of dr over square root dr. Lambda theta, exact same thing. Integral from theta min now to pi minus theta min. So that's the maximum you can get. And the integral is over square root of e theta. So these plus and minus signs over here correspond to inward and outward motion. Now we also have the period of the azimuthal motion. Which I'll call lambda phi. And so that's just an integral over one passage from 0 to 2 pi. D lambda d phi, d phi. And in terms of the v's, this is an integral from 0 to 2 pi of d phi over v phi. So all these are the periods of menotime lambda. Now remember, for Schwarzschild orbits, or Schwarzschild geodesics, you had closed orbits when you had a ratio between tr and t phi that was rational. So the one over the other was a rational number. And that's called an extrinsic resonance. It's an extrinsic resonance because the intrinsic dynamics don't actually depend on phi. Phi doesn't appear on the right-hand side of any of those equations of motion. And that's a consequence of the axial symmetry of Kerr and of Schwarzschild. So those do end up having a significant impact, or a not insignificant impact, on the evolution of a memory. Because what happens is, as you evolve an memory, the frequencies change with time. They change slowly with time. And then every once in a while, the frequencies will have a rational ratio, and you'll have a resonant outcome, and then you keep evolving out of the resonance. Eventually you'll reach another resonance, evolve through that, and so forth. But those do not have a big impact. What does have a big impact is when these periods have a rational ratio, because r and theta are intrinsic quantities in the dynamics. So if there exist integer numbers nr and n theta, then there's an intrinsic resonance. So this is where you don't get a closed orbit in all 3 dimensions, but if you're just looking at the radial and theta motion, it closes in the r theta plane. And this has a big impact on the dynamics. I'm not going to go into the details, but remember early on I said you needed the full first order self-force and the dissipative piece of the second order self-force. So that comes from an approximation for the phase of the orbit. Let me say phi of this form is the phase, the total phase of the orbit, or the phase of the gravitational waveform. That has a form that I'll get back to in a second, but it's roughly of this form. And this is the form in the absence of resonances. So it starts at 1 over epsilon because the phase accumulates roughly linearly in time. So if you wait for a full inspiral, which is order 1 over epsilon time, your phase also has 1 over epsilon accumulated. Then for this piece, it turns out all you need is a certain bit of the first order dissipative force. For this piece, it turns out you need the full first order force and a certain dissipative piece of the second order force. But this is all in the absence of resonances. If you pass through one of these intrinsic resonances, you actually get a new term in the middle, square root of epsilon. And that's if you have just one passage through one of these intrinsic resonances. And what happens at resonances is that information flows from higher order down to lower order in this approximation. So to get even this square root of a half term, you need the second order dissipative force. And if you go through a second intrinsic resonance, actually that information about the second order dissipative force feeds into the leading order term because you keep bumping up half an order with each resonance. And a full inspiral from infinity to plunge into the big black hole's horizon, you actually pass through an infinite number of these resonances. So you'd think, okay, that totally destroys our entire approximation scheme. We need to go to infinite order in perturbation theory, which would be obviously very, very bad for us. We can't do that. It turns out that only low-order resonances, where nr and n theta are both between 1 and 3 or so, only those have a real big numerical impact on your final result. And a typical inspiral will only pass through one such strong resonance. So that gives us hope that we have enough to do the accurate modeling. Okay, that's all I'm going to say about resonances. So that's based on sampling the phase space and actually doing approximate evolutions and seeing how many you pass through. And so Scott Hughes did a sampling of the full phase space, and he found that generically you will pass through one, but only one. If you pass through two, then our modeling breaks. We don't have enough accuracy to do what we want to do. But it's a very small percentage that passes through two. Okay, so yesterday we were looking at the first order field equation, and I said we can approximate the small object as a point particle source on the right-hand side. And then I said, okay, at leading order, we have geodesic motion, so let's look at geodesics. But now, let's talk about how we actually include the evolution away from geodesic motion. So the accelerated motion that occurs due to the self-force. So there are a few different ways of doing this. I'll describe 3 ways. So first, the thing you need to realize is that the motion is coupled to the field, because the motion of the particle determines what field is produced, and then the field that's produced determines what the motion of the particle is. So the two things are coupled to each other, and that complicates the analysis of the field equations somewhat. But the key thing is, we need to decide how to describe the orbit before we can decide how to describe the metric perturbation. Okay, so the first method, which is conceptually maybe simplest, is probably the method that most people would think of first, but really only these two people have actually used it consistently to derive results. So that's Sam Gralla and Bob Wald. And the idea here is that you really just do expand everything in a Taylor series. So your world line, your accelerated world line, is a function of tau, or whatever parameter you want to use, and of epsilon. So you just perform a Taylor series expansion of that. So each of the coefficients here do not depend on epsilon. So what's actually being described here? Let's say Z0 is a circular orbit. So this is Z0. Then Z1 and Z2 are actually vectors that live on this orbit. They're defined on this orbit, and they're pointing towards the accelerated curve. So you have, say, Z1 alpha here. Sometime later, you have Z1 alpha here. So I'm drawing a very exaggerated picture where you're inspiraling very rapidly. So here's the central black hole. Here's the particle going around. Okay, so what happens when you work with this kind of description of the motion? So here you can show that this leading order piece is a geodesic of the background. So for us, it's a geodesic of the Kerr black hole spacetime. Then the metric perturbation is a function of coordinates and of epsilon. We also just write as a Taylor series. The first order piece depends on the zeroth order geodesic motion, but does not depend on any of the corrections. And it can't because it has to be independent of epsilon. Now the second order piece depends on Z0, but it also depends on the correction to the motion. So then the Einstein equations you end up solving. You have linearized Einstein tensor equal to 8 pi T alpha beta. And this is the stress energy of a point particle moving on the zeroth order geodesic. Then at second order, you can schematically think of having a second order stress energy tensor, which now will depend on Z1. So this is the correction to the point particle stress energy due to the deviation Z1 away from Z0. And we also have the quadratic combinations of H1 as source terms. Okay, so what are the equations of motion for Z0, Z1, and so forth? So as I said, you can show that zeroth order piece is just a geodesic. The first subleading piece, so it has this first order self-force that I mentioned on the right-hand side. But now it also has a Riemann term And you might recognize this as what appears on the right-hand side of the geodesic deviation equation. Yep. Yep. This piece? Why does this not evaluate to 0? Why would it evaluate to 0? So this is the metric perturbation produced by a point particle moving on a geodesic. It's not a test particle, it's a point particle with mass. And that mass produces this metric perturbation. Does that make sense? Why is there no zeroth order term in H alpha beta? So the zeroth order term is G alpha beta. So here I'm only expanding the metric perturbation H. Right? So the full metric is G alpha beta plus H. Does that answer? Okay. Yeah, so this geodesic deviation term appears, and that's because as soon as the self-force forces the particle off of this geodesic world line, well then curvature acts to keep moving it around relative to the zeroth order world line. So it physically makes perfect sense that that's there. Okay, but what's the problem with this type of expansion? The problem is, you can see from this picture that eventually Z1 is getting huge. Z1, or epsilon times Z1, has to point from the initial geodesic all the way inside the black hole, which is an order 1 distance. So actually Z1 by itself is growing to order 1 over epsilon. So this expansion is only valid on a short timescale. For a timescale that's much, much shorter than the long timescale of the inspiral 1 over epsilon. So this is an expansion that's designed to work on the orbital timescale, not the full inspiral radiation reaction timescale. Okay, so this breaks down after a short timescale. So you don't want to use this as a global description of your emery. It's not going to work. Okay, another method is called the self-consistent approach. And here the basic idea is you just don't expand Z alpha. You just treat it as some exact function of tau and epsilon, and you try to avoid expanding it. So that means that the metric perturbation is now going to have a different kind of expansion. Where now it's a function of where you evaluate it, but it's also a function of this full accelerating orbit, Z. And each term in the expansion is going to keep on depending on that accelerated orbit, and so on to higher order. Okay, so z depends on epsilon, which means that the coefficient h1 also depends on epsilon, and coefficient h2 also depends on epsilon. So this is no longer a Taylor series. It's an asymptotic series in the sense that each term is smaller than the last when epsilon is small, but it's not a Taylor series. So the kinds of equations you get in this case are of this form. So now the first order metric perturbation, actually, did I introduce this E in previous lectures? No? Okay, so E here is box h bar alpha beta plus 2 r alpha mu beta nu h bar mu nu. So this is the Lorentz gauge linearized Einstein operator. So on the right-hand side now we have a point particle that's moving on the accelerated world line, not on the 0th order geodesic. And then in second order, you can think we have, again, some second order stress energy tensor, although we'll get back to issues involving the stress energy tensor a bit later. And now the quadratic terms are constructed from the h1 that is sourced by the accelerating particle. In addition to this, you have the Lorentz gauge condition that allowed you to write the left-hand side in terms of this wave operator. So there's a constraint which is that the sum of all these pieces of the metric perturbation have to satisfy the Lorentz gauge condition up to third order, up to third order errors. This does not apply, or it does not imply that the divergence of h1 is identically 0, the divergence of h2 is identically 0. Those are not true statements, and that's because you have epsilon dependence in Z, which gives you epsilon dependence in H1, and so here you can't just identify 0th order term, or sorry, first order term, second order term, each individually 0. You need to actually add them all up. But the Lorentz gauge field equations here are constraint preserving, which means that if this is satisfied on your initial data slice, it's automatically going to be satisfied to the future of that initial data. So the equation of motion here, rather than getting a sequence of equations for Z0, Z1, Z2, and so forth, the equation of motion is just of the form that I wrote down originally, that the covariant acceleration is epsilon f1 alpha, and this f1 alpha is constructed from h1, and you'll have second order terms and so forth. So this is actually directly a coupled system of equations. You need to know how Z is accelerating to find out what the source is for the first order metric perturbation, and you need that metric perturbation to find out how the orbit is accelerating. So it's coupled, you need to solve them all at once or self-consistently, which is why it's got the self-consistent title there. Okay, so this approach does accurately track the motion. You don't get this kind of blow up due to having Z1 growing big. Now everything is well behaved. So So here everything's well behaved. But not that practical. So here, the only obvious way to actually obtain the metric and the motion is just to solve these coupled equations in the time domain numerically. And because we need to track hundreds of thousands of orbits, that's a very daunting numerical task. And I don't think anyone is ever going to be able to do it. So what I think is much more practical is a 2-time scale approximation. So here we make use of the fact that our system has 2 distinct timescales. One is the orbital period, and one is the time of inspiral, or the radiation reaction time. So these are very distinct timescales that have very different scales. One is epsilon times, or 1 over epsilon times the other. So we take advantage of that. We first introduce a set of orbital parameters, E, Lz, and C. But these are going to be evolving with time in a particular way. And we have a set of phases, psi r, psi theta, psi phi. And these j's, the constants of motion, which are no longer constant, evolve with time, but slowly. They evolve on the radiation reaction time, not on the orbital time scale. So let's write that as J alpha of T and epsilon. Here I'm thinking of coordinate time, but really you could do this with any parameter, is J0 of T tilde plus epsilon J1 of T tilde, and so on to higher order, where this T tilde is just epsilon times T. It's called slow time. So when T is of order 1 over epsilon after radiation reaction time, T tilde is of order 1. So these are evolving on the radiation reaction time, but they're approximately constant on an orbital period. Then the phases satisfy d psi dt is omega alpha, where this omega is just 2 pi over the orbital period that I described before. And we can arrange things such that this orbital period, or sorry, this orbital frequency has an expansion just like the constants of motion. So we can write each term in the expansion in terms of the constants of motion. So we have a 0th order frequency that only depends on the 0th order E, L, and C. Then we have a correction to that frequency that depends on the correction to the constants of motion E, L, and C. And everything's evolving on the slow time scale. So this is where the formula I wrote 15 minutes ago came from. if you just integrate this equation, you find that each of these phases has an expansion of the form I showed before. So we just integrate against t, but each of these are functions of slow time. So let me change the integration variable to t tilde. That introduces 1 over epsilon. So now we have the expansion I showed you before. We have an overall 1 over epsilon, and then we have a psi 0 that comes from the integral of this. Plus order epsilon correction that comes from the integral of omega 1. And so forth to higher order. Now, if you had an orbital resonance in here, you'd have a square root of epsilon term, and that would give you a square root of epsilon term here, and a square root of epsilon term here. But right now, we're just ignoring resonances. Okay, so this kind of expansion actually tells us what we need to get the phase to a certain order. And it tells us what I described before, that you need only the dissipative first order force to get psi 0, and that's because you only need that piece to get J0, or the evolution of J0. And then you need the second order dissipative and first order conservative to get psi 1, and that's because those are the terms you need to get J1. Yep. Okay, I'll say a bit more about the 2-time scale expansion. So that's the treatment of the motion, but what does this mean about the metric? Okay, so first, let's make that more explicit in terms of what it means for the motion. It means that the world line, the accelerated world line, has this form. You have a 0th order piece that depends just on the 0th order piece of energy, angular momentum, and Carter constant. And now it's a periodic function of the phases. These are the exact phases. These are not geodesic phases. This is the exact phase. So this term is periodic in the true phases of the final inspiral. And then we have an epsilon times Z1. So again, this is not the Z1 that appears in the Grella-Wald approach, because this depends on a slowly evolving J0, a slowly evolving J1, and again, it's periodic in the phases of the evolving orbit. So Z1 here never gets big. The epsilon times Z1 remains of order epsilon the entire inspiral. But this functional dependence on J0 and psi is the same functional dependence you have for a geodesic. So a geodesic would just take this J, make it constant, and take this phase and make it omega times t. But it's the exact same dependence on these two variables you'd have for a geodesic. It's just that the variables themselves are evolving in a different way than they would be for a geodesic. Okay, so what is happening with the metric perturbation? So the metric perturbation is epsilon h1, function of coordinates, but only of some coordinates. So this is just r and theta. It's a function of t tilde. It's a function of the J0s and a function of the size. And again, it's exactly periodic in the phase variables. Then we have second order term with the same structure, epsilon squared, h2 alpha beta, xa t tilde, j0, but now we also have a dependence on j1. Sorry, this should also depend on phi. And the ansatz is that this structure just carries on indefinitely. So you always have something that's periodic in the phases, and then it's slowly evolving due to the slow evolution of the orbital parameters. And then there's additional slow time dependence coming from, for example, the fact that the big black hole is actually growing with time because it's absorbing gravitational radiation. So the mass of the big black hole is slowly changing, and that becomes a correction to the metric that appears in H1, and it depends on slow time. So you have some small amount of slow time dependence that isn't just coming from the evolution of the orbital parameters. Okay, now the Einstein equations. So the test particle limit you'd only define on a short time scale, because the accelerated curve is always going to go far away from the test particle orbit once you wait for a long enough time. So for the test particle limit, you would take epsilon goes to 0 and the short time expansion, and all three would give you that same result. The leading order, you have 0 metric perturbation, because the metric perturbation is proportional to epsilon, and you have geodesic motion of the test particle. So you're looking at short times. Over a short time, it hasn't grown by much. Yeah. Even after a full inspiral, it's only growing by an amount of order epsilon. So over a short time, it's actually growing by epsilon squared. Okay. Now I'm going to write these as Fourier series, taking advantage of the fact that they're periodic in the phases. So I'm going to write Hn alpha beta is a sum over oscillatory phase factors with amplitudes nk alpha beta depend on xa and slow time. So here I'm dropping the explicit dependence on J0 and just absorbing that into whatever the full slow time dependence is. So slowly evolving amplitudes with a phase factor e to the minus I k alpha psi alpha. So when we have expansions of this form, and we put them into the Einstein equations, we'll put them into, say, these Einstein equations, then what you get is just equations for the amplitudes. The phases just completely factor out. So how am I going to write this? So here I'm going to put 0k. So the k corresponds to this k. You're looking at the kth amplitude. And the 0 means when I operate with the linearized Einstein tensor on H, I'm just ignoring derivatives of the slow time dependence. The reason I'm doing that is if I operate with a t derivative on some function of slow time, then that's dt tilde dt times ddt tilde of h, but this is just epsilon. So when a time derivative acts on a function of slow time, it gets suppressed by order epsilon. So all these order epsilon terms coming from slow time derivatives, I'm going to move into the second order Einstein equation. Here I'm just ignoring them. Also, when you act on these phases, these phase factors, you just bring down minus I k alpha omega alpha times the phase factor again. Remember, these frequencies are just the time derivative of psi. But then this omega alpha has expansion like that, where it's got a zeroth order term, a first order term, and so forth. So this 0 in here also means that I'm dropping this omega 1 term and higher order terms and just keeping the omega 0. And then the omega 1 term, just like the slow time derivatives over here, just get moved into the second order equation. And so the argument here is 1k. So this is an equation for the kth amplitude of the first order metric perturbation. And again, the phase factor has just entirely canceled out on left and right hand sides. And then you substitute the expansion of the motion into the stress energy tensor. You can again pick off a leading order piece, and this is again an amplitude, a coefficient of e to the minus ik alpha psi alpha. That amplitude only depends on J0, the leading order orbital parameters. Then at second order, we're going to have a similar equation, but now those terms that I was excluding on the left-hand side are now going to get moved over to the right-hand side and be sources. So here we're going to have the same operator on the left-hand side, linearized Einstein tensor, or the kth mode of it. And now it's acting on the kth mode, or the kth amplitude of the second order perturbation. Now we still have the second order Einstein tensor. I'm looking at the kth amplitude of that. And again, the 0 means I'm dropping omega 1, and I'm dropping slow time derivatives. So these are constructed, or this piece is constructed from the mode amplitudes of the first order field. It doesn't depend on the phase factors out of everything. Now I have terms that are either linear in a slow time derivative or linear in omega 1. So I'm going to write that as 1k and it's acting on h1k. One subtlety here is that this should not be the same k inside. There should be k prime. This is quadratic, so it's actually a sum over products of first order modes. To get a single amplitude here, you need all the first order amplitudes. So again, this is basically dt tilde plus omega 1 type terms. Okay, so because the phase factors have just factored out entirely, these are just frequency domain equations. You only have dependence on r theta phi. You don't have dependence on fast time, or t at all. So this equation here is exactly the same equation you'd have if you just put in a geodesic test particle, or geodesic source term here, and just decomposed into frequency modes. You'd get exactly the same equation that you've got here. It's just that now everything is a function of slow time that we evolve with slow time. But the idea is to solve this at a fixed value of slow time, to get the amplitudes of that slow time, and then evolve forward to another slow time, get the amplitudes of that slow time, and so forth. How do you evolve from one slow time to the next? That partly comes from the equation of motion. So this equation of motion becomes the equations we had written over there. But now let's write them in terms of pieces of the metric perturbation, more explicitly. So we have the slow time evolution of J is a quantity, no, let me use a different symbol. It's a quantity constructed from this F1, but it's not exactly that F1. It's now, each of these is constructed from just the mode amplitudes of the first order field. Okay, and the phase factors just cancel out. Then you have an evolution equation for J1. Which I'll write in kind of schematic form here again. Again, only depends on the amplitudes and not on the phases. So this tells you how to evolve from one slow time to the next. Because remember over here, my H1 depends on slow time through J0. So if I know how J0 evolves, I can then update to the next slow time. I also mentioned that there's other slow time dependence related to the change of the black hole parameters. So you need to combine these with equations for the correction to the big black hole's mass, and you can actually find what this equation is directly from the second order Einstein equation. But it's basically the gravitational wave energy flux into the big black hole. And you have a similar equation for the correction to the big black hole's spin. That is the angular momentum flux into the black hole. So these tell you how to evolve to the next value of slow time. And in this entire process, you don't need to actually know how the phases are evolving with time, because they've just factored out. But then at the end of the day, once you've found all of these as functions of slow time by evolving from one time step to the next, you can then extract the very end, all the phases from J0 and J1 just by using this. So you now know how these evolve with slow time, so then you know how the frequencies evolve with slow time, and then you just integrate to get the evolution of the phases. Then say you want the waveform. You just take those phases you've got. You've already calculated the amplitudes, slow time step by slow time step. You now know the phases. So if you want to look at the leading order waveform at infinity, you just pick off h1, you put in the time dependence of the phases here, and that gives you your waveform at infinity. All right. So the two-time scale approach is kind of how you should be thinking about the problem going forward. But there's a forerunner to the two-time scale approach, which is actually just the leading order piece of the two-time scale approach, and that is the adiabatic approximation that I mentioned on Monday. So let's look at adiabatic approximation. And let's specialize to Schwarzschild. So in general, the adiabatic approximation would mean just calculating this leading order piece of the frequencies, from that extracting the leading order piece of the phases. So that's called adiabatic order, and then this next term is post-adiabatic order, or first post-adiabatic order. So the resonances, if you only encounter one, they just introduce a square root of epsilon term here. So they're post 1/2 adiabatic order. Okay, the reason we're going to restrict to Schwarzschild is that the adiabatic approximation in Kerr requires the evolution of the Carter constant. And to figure out how that evolves, you actually need to go into the equation of motion with self-force, which we haven't actually written down explicitly yet. And there's a long, complicated procedure to extract just the piece you specifically need to get this leading order evolution of the Carter constant, and then from that get the full evolution of the phase. But in Schwarzschild, you actually don't need to know anything about the self-force to get the adiabatic approximation. You just need to make energy balance arguments and angular momentum balance arguments. Okay, so the basic idea you first just choose some value of energy and some value of the z component of the angular momentum. And then this specifies for you a geodesic up to trivial rotation in the equatorial plane. So restricting to the equatorial plane, E0 and L0 gives you a unique geodesic. So that's step one. Step two, you calculate gravitational waves at infinity and at the event horizon as if they were sourced by a point mass moving on that geodesic. So you think this is a good approximation for short chunks of time. Because for short chunks of time, the motion is pretty close to a geodesic. Actually, continue on with that. So from the gravitational waves, you extract how much energy is being carried out of the system at infinity, and how much angular momentum is being carried out of the system at infinity, and also how much energy is being carried in to the black hole through the horizon, and similarly for angular momentum. So say we've got our big black hole here, we've got our point mass moving around in an orbit on a geodesic. That's radiating gravitational waves that go to infinity and create these fluxes of energy and angular momentum. But then you also have gravitational waves being absorbed by the big black hole. So over here at the horizon, you calculate the rate of change of energy and angular momentum that's going into the big black hole. And out here, you calculate the amount carried out to infinity. Then the idea is anything that leaves the system out here or falls into the black hole here has to be coming from the particle. It has to be coming from the kinetic energy and the orbital angular momentum of the particle. So the next step is to assume balance laws. So using the actual explicit formula for the self force, you don't need to assume balance laws, you can prove them, but for now let's just assume them. So the balance laws are that the energy of the particle, how much it's changing, is just the opposite of the energy carried away from it in the form of gravitational waves. So anything that leaves this zone has to be coming from E0. And similarly for L0. So now once you have that, you can update the values of E0 and L0. So you can think, okay, there's a new value of E0, which is the value you started with, plus that E dot naught times a little step in time. And same for angular momentum. L dot 0 delta t. Then you just repeat. You now have a new geodesic with these new parameters. You put a test particle, not a test particle, you put a point mass on a geodesic with these parameters, you calculate the gravitational waves, you get a new E dot and L dot, you move forward to the next time. You just keep doing that. So just repeat as many times as you like. And then finally, at the end of the day, you extract the phases, or the phase. So here the phases are the radial phase and just the azimuthal angle. From psi r is the integral of omega 0 dt, and psi phi is the integral of omega 0 phi dt. So this description is exactly equivalent to just doing the 2 timescale expansion and just keeping everything at leading order. Even though the physical description I've given is somewhat different, it's exactly mathematically equivalent. Okay, so the first thing you need to know then is how do we actually calculate these E dots and L dots at infinity and at the horizon? So for this, you need to define what you mean by fluxes of gravitational wave energy and angular momentum. Define what we mean by that. So first, rather than gravitational waves, let's just consider a general matter source. So it's just some source. This is not the point particle. This is just a generic, smooth stress energy tensor. We can define the energy in a spatial slice let me just call it region, the spatial region sigma. Do I have room to write it here? Yeah, I'll write it right here. The energy contained in that region is E equals minus the integral over that region of T alpha beta contracted into Z beta of T. This is the time-like killing vector. And then a directed surface element, d sigma alpha. So this is a future directed surface element. So let's draw the surface we've got here. This is sigma. And we have a future directed surface element and alpha. And basically, d sigma alpha is n alpha d sigma, I think with a minus sign. Yes, with a minus sign. Okay, so this is the energy on one surface. And now let's consider a tube. And let's call this time sigma 2. And this is time sigma 1. And each of these surfaces are going to be a surface of constant coordinate t. And let's make this boundary of the tube a surface of constant r, radial coordinate r. Okay, then the question is, how much is the energy changing between this surface and that surface? So the energy of surface 2 minus the energy of surface 1 is just the difference between two of these integrals. Let me write this a bit more explicitly. This surface element, you write as n alpha square root of f r squared dt d omega. And this n alpha, the unit normal, is 1 over square root of f. I'm skipping a step here. This we call S out, the surface of constant radius. The boundary of the tube is S out. So what we want to do is convert the difference between two integrals to an integral over S out using Stokes' theorem. And let me change the name of this because I'm using n for two different things here. Let me just call this T alpha. This is minus T alpha. Okay, so as an exercise, you can prove this relationship. Just use Stokes' theorem. So the difference between this integral at sigma 2 and the same integral at sigma 1 is an integral over the boundary of the tube, S out, where now this is the outward directed surface element, radially outward. So if you've taken a advanced GR class, you've probably actually already seen the proof of this. Okay, now I need to get that down there. So ds beta, the outward directed surface element, is n alpha square root of f r squared dt d omega. So dt d omega is just the natural element on the surface. You're going up in t, and you're going around in angles. And this is the radially outward directed unit normal, which is 1 over square root of f delta r alpha. So this square root of f cancels that square root of f. And you just have delta r alpha r squared dt d omega. So this is just the flat space surface element of a surface of constant r. So all the Schwarzschild factors cancel out. So if we plug that in, and if we plug in that z beta t is just delta beta t, then what we've got here is t r t dt r squared dt d omega. And that is the integral of minus the integral over just a sphere, t r squared d omega, then the integral over t. So this is the change in energy over a finite amount of time. So then what does that imply about the instantaneous change of energy? Well, it's got to be just this thing in parentheses, because when you integrate that up in time, you get the change over a finite time. So this bit here has to be E dot. So this is for just an arbitrary smooth stress energy. Now let's apply that to gravitational waves. So just to emphasize, E dot is minus r squared f. I'm just bringing out that f because I'm going to lower this index. Now it's t with index down. D omega. Okay, similarly, the angular momentum on one of these surfaces is T alpha beta, and now contracted into the azimuthal Killing vector. And the exact same calculation gets you that L dot Z is r squared f times the integral over a sphere of tr phi d omega. So let's apply these at infinity, where we're going to calculate the flux of gravitational waves. So E dot at infinity is minus the limit, so r goes to infinity, of r squared f And this is a sphere of radius r, t, t, r, d omega. So this is just evaluating this formula at infinity. And similarly, if we evaluate the angular momentum flux at infinity, we have limit r goes to infinity of r squared f integral over a sphere radius r tr phi d omega. But now we also want to include a boundary around the black hole. So let me put another tube inside this bigger tube. Let me call this S in. Then you go through the same calculation. Now we're looking at S in, and you find E dot at the horizon, so we're putting S in at r equals 2m, is the limit as r goes to 2m, r squared f integral over sphere of radius r. So the only thing that's changed is I'm now evaluating a different place, and also there's an overall change in sign, because outward means two different things depending whether you're looking at the outside tube or the inside tube. And same thing for L dot at the horizon. Get an overall sign change. And we evaluate at 2m r squared f t r phi d omega sr. Okay, so we're not going to get to define what I mean by the stress energy tensor of the gravitational waves, but we'll get to that tomorrow and finish this up. Okay, questions? Yeah, so the energy of gravitational waves is only defined on average. It's not defined instantaneously. Exactly, these things are only going to hold when you're looking at averages over some chunk of time. So in our case, averages over orbital cycles. For the gravitational waves, yeah. You can only think about averaged amounts passing through a surface. You can't think about instantaneous amounts passing through a surface. Yeah. Anything else? Yeah. So this is the changing Bondi mass of the system. This is the changing Bondi. Oh, wrong. That is the changing Bondi mass. This is the changing Bondi angular momentum. Yeah. So the Bondi mass loss formula tells you that the rate of change of the Bondi mass is just the flux of gravitational waves out to infinity, which is exactly what we're calculating. Yeah. So this is what's changing the mass of the black hole. It's the energy that's falling into the black hole. So this is changing, but that doesn't affect the adiabatic evolution. So this, in the 2-time scale framework, this and this both lead to order epsilon corrections to the metric that are slowly changing with time, corresponding to small changes in the mass and angular momentum of the big black hole. So they're order epsilon corrections, so you'd think they'd go into H1 and then they would affect E dot infinity and L dot infinity because they're in H1. You might think that. But it doesn't happen because they're stationary perturbations, so they don't create waves. So they don't contribute to the fluxes at infinity. You mean the change in the big black holes? So it's order epsilon. So it's order epsilon in the metric perturbation, but order epsilon squared in the rate of change of the Bondi mass, for example. That's it. All right, thank you.